Summer 1932. Romney Marsh, Kent, England. An operator named Collins sat in complete darkness beneath a 30-foot concrete dish, stethoscope-style earphones pressed against his ears. His colleague stood 200 yards away at another mirror, a vertical wall stretching 200 feet across the marsh like something from an alien world. The English Channel stretched before them, silent. Then Collins heard it, a low, distant drone, barely perceptible. He adjusted his position slightly, moving the microphone millimeter by millimeter along the focal point. The sound sharpened, grew louder, more distinct. "Contact bearing 270, elevation angle 15 degrees, he reported into the communication tube. 20 miles away, invisible to every telescope and human eye on Britain's coast, a formation of bombers cut through the dawn sky at 100 miles per hour. Collins had just detected them. The mathematics were brutal and beautiful. 20 miles divided by 100 miles per hour equals 12 minutes of warning time. 12 precious minutes before radar existed. This is the forgotten story of Britain's acoustic mirrors, concrete monsters that could hear death approaching from beyond the horizon. But more importantly, this is about the operators who learned to translate whispers of sound into coordinates of survival, and the brilliant engineer who created a detection network that would teach Britain how to track enemies in three-dimensional space. What they built wasn't just an early warning system. It was the blueprint for radar itself. To understand why Britain covered its coastline with concrete ears, we need to go back to 1915. The Great War brought something terrifying: death from above. German Zeppelins floated over England like silent whales, dropping bombs on cities with impunity. Traditional defenses were useless. By the time someone spotted a Zeppelin visually, it was already overhead, bombs already falling. Britain faced an impossible problem. How do you defend against something you cannot see until it's too late? Enter Dr. William Sansome Tucker, a British Army officer with a background in acoustics. Tucker understood something fundamental. Sound travels at 767 miles per hour at sea level, but aircraft in 1915 flew at only 60 to 80 miles per hour. This meant the sound of an approaching aircraft would arrive nearly 10 times faster than the aircraft itself. Sound could be your early warning, arriving minutes before the danger. In 1915, Tucker constructed Britain's first experimental acoustic mirror at Binbury Manor near Maidstone, Kent. The concept was deceptively simple. Create a curved concrete surface that would collect sound waves and focus them onto a single point, like a satellite dish, but for audio instead of radio signals. Place a microphone at that focal point, and you could detect aircraft engines from extraordinary distances. The first operational mirrors went up in 1916 along Britain's southeast coast. They were modest, perhaps 15 to 20 feet in diameter, but they worked. Operators reported detecting Zeppelin engines at ranges of 8 to 12 miles, providing 10 to 15 minutes of warning time. For the first time in military history, Britain could hear the enemy coming before anyone could see them. After the war ended in 1918, Tucker didn't stop. He became obsessed with perfecting the technology. Throughout the 1920s, he experimented with different designs, different sizes, different configurations. The Air Ministry funded his research, convinced that acoustic detection represented Britain's best defense against the growing threat of bomber aircraft. By 1928, Tucker was ready for his most ambitious project yet: 3 experimental mirrors at Denge near Denge in Kent, each testing a radically different approach to acoustic detection. The stage was set for Britain's greatest experiment in sound-based warfare. The fundamental challenge facing Tucker's acoustic mirror program was brutally simple, yet seemingly impossible to solve. Detect a bomber flying at 100 miles per hour from at least 15 to 20 miles away in all weather conditions, and determine its exact location in three-dimensional space: altitude, bearing, and distance. Let's break down why this was extraordinarily difficult. Challenge 1. Aircraft were getting faster. In 1916, Zeppelins lumbered along at 60 miles per hour. By 1930, the newest bombers, like the Ferry Battle, could reach speeds exceeding 250 miles per hour. Physics became Tucker's enemy. At 15 miles detection range, a 250-mile-per-hour bomber would cover that distance in just 3.6 minutes, barely enough time to scramble interceptors, much less coordinated defense. Tucker needed to push detection range beyond 20 miles to achieve meaningful warning times. At 20 miles, even a 250-mile-per-hour bomber would take 4.8 minutes to arrive, while a 100 miles per hour bomber would take 12 full minutes. Every additional mile of detection range translated directly into precious seconds of warning time. Challenge 2. Sound doesn't travel in straight lines. Unlike light waves, sound waves bend, refract, and dissipate based on atmospheric conditions. Temperature gradients cause sound to curve upward or downward. Wind could carry sound away from the microphones or distort its direction. Humidity affected how far sound could travel before degrading into inaudible noise. Tucker's operators faced an infuriating reality. On a cold, still morning with perfect atmospheric conditions, they might detect an aircraft at 20 miles. But on a windy afternoon or during a storm, that range could collapse to just 5 miles, useless for early warning purposes. Weather wasn't an obstacle, it was the enemy. Challenge 3. The ocean roared. Romney Marsh sits directly on the English Channel, where waves crash constantly against the shore. That ambient noise created what acousticians call a noise floor, a baseline level of sound that drowns out quieter signals. Aircraft engines at 15 miles generate very faint sounds. The challenge was amplifying those whispers while filtering out the thunder of surf. Tucker needed microphones sensitive enough to detect a whisper from 20 miles away, yet capable of ignoring the roar happening 100 yards behind them. Challenge 4. Three-dimensional location. Hearing an aircraft wasn't enough. Defense commanders needed exact coordinates: bearing, which direction, altitude, how high, and ideally distance, how far. A single acoustic mirror could only provide bearing, the direction the sound was coming from. It couldn't tell you whether the aircraft was at 5,000 feet or 15,000 feet. It couldn't definitively tell you if the plane was 10 miles away or 20 miles away. This required multiple mirrors working in coordination, triangulating the sound source from different positions. The mathematics were complex. The coordination requirements were even more complex. Tucker needed to create not just individual listening posts, but an interconnected network that could share data and calculate positions in real time. In 1928, this was cutting-edge computational challenge. Challenge 5. The human element. All the concrete and microphones in the world meant nothing without skilled operators. Tucker needed people who could distinguish aircraft engines from ships, motorcycles, distant trains, and tractors, maintain intense concentration for hours despite hearing nothing, make split-second identifications while sleep-deprived and cold, operate equipment with precision in darkness and terrible weather, coordinate with other stations via primitive communication systems. Finding and training these operators would prove as difficult as building the mirrors themselves. In the summer of 1928, construction began at Denge on 3 wildly different mirror designs. Tucker was about to test whether human ingenuity could overcome the laws of physics. But what he didn't know was that someone else was about to make his entire program obsolete.
Between 1928 and 1930, 3 extraordinary concrete structures rose from the marsh at Denge. Each represented a different theory about how to capture sound from the sky. The 20-foot mirror, the conservative approach. Completed in 1928, the 20-foot mirror looked like a shallow concrete bowl, roughly 6 meters in diameter. This design evolved directly from Tucker's World War I prototypes. The parabolic dish focused sound waves onto a microphone mounted on a metal pole at the focal point. The operator sat in a small chamber behind the mirror, listening through stethoscope-style earphones. To change the direction of listening, the operator physically moved the microphone along a tracking mechanism, sweeping it across the focal plane until the sound reached maximum intensity. A grid marked on the mirror's face indicated altitude and bearing based on microphone position. Detection range: 10 to 15 miles under optimal conditions. The 20-foot mirror was reliable, but limited. The 30-foot mirror, the precision instrument. Completed in 1930, the 30-foot dish represented Tucker's evolution in design. At roughly 9 meters in diameter, this parabolic mirror was significantly deeper than its smaller cousin, creating a tighter focal point. The increased size meant it could collect more sound energy, theoretically increasing both range and accuracy. The operator descended a flight of concrete steps into a chamber directly beneath the dish, like working inside the bell of a massive horn. The step's height reveals something fascinating. Over the decades, the ground level around the mirror has fallen several feet due to erosion, but the steps remain, showing the original surface level. The microphone mounting system was more sophisticated, allowing finer adjustments. The metal pole extending from the focal point still stands today, a rusted finger pointing at the sky. Detection range: 15 to 20 miles under optimal conditions. This became Tucker's workhorse design. The 200-foot mirror, the audacious experiment. Completed in 1930, the 200-foot mirror was Tucker's masterpiece and his most radical gamble. Instead of a circular dish, he constructed a curved wall stretching 200 feet long and 26 feet high. This wasn't a parabolic curve. It was a spherical mirror segment based on entirely different acoustic principles. The wall's immense size created challenges the smaller mirrors didn't face. To operate it effectively required a minimum of 3 people, 2 operators in front of the mirror moving microphones along a listening trench, and 1 coordinator in a building behind the structure managing communications and calculations. Why build something so enormous? Surface area. The 200-foot mirror could capture vastly more sound energy than any dish-style mirror. Tucker theorized this could push detection ranges beyond 20 miles, perhaps as far as 25 or even 30 miles, giving Britain unprecedented warning times. Detection range: 20 to 25 miles claimed under optimal conditions, though verification of these claims remained controversial. The operator's challenge: learning to listen. In the summer of 1932, the Royal Air Force began formal training of acoustic mirror operators at the Hythe facility. These men faced a learning curve unlike any military training program of the era. Training began with basic acoustic recognition. Operators listened to recordings of different aircraft engines until they could identify types by sound alone. A Bristol fighter had a distinct growl. A Hawker Hart had a sharper, higher pitch. German bombers had different acoustic signatures than British ones. But recordings in a classroom bore little resemblance to reality. Sound arriving from 15 miles away, filtered through atmosphere, wind, and ambient noise, transformed into something barely recognizable. Operators had to learn to hear patterns within chaos, recognizing the rhythmic pulse of a rotary engine beneath the hiss of wind, or distinguishing the Doppler shift of an approaching aircraft from the steady drone of a ship. The work demanded almost superhuman concentration. Imagine staring at a blank wall for 6 hours straight, looking for a specific shade of gray. That's what acoustic mirror operators did with sound. Hours of silence punctuated by faint, ambiguous noises that might be an aircraft, or might be a fishing boat, or might be nothing at all. False positives carried consequences. Call too many alerts, and commanders would ignore you. miss a genuine contact, and bombers could reach London unopposed. The operators developed techniques that bordered on mystical. They learned to position their heads at micro angles to maximize clarity. They discovered that closing their eyes helped focus auditory perception. Some claimed they could feel the sound vibrating in their chest before consciously hearing it in their ears. Operating the 200-foot mirror required choreography. Two operators worked in tandem, moving along the listening trench with their microphones, calling out bearing adjustments, while the coordinator behind them plotted positions on a large board. When both operators achieved maximum signal strength, the intersection of their bearings indicated the aircraft's direction. Cross-referencing with other mirror stations could triangulate approximate altitude and distance. Communication between stations happened via telephone lines, slow by modern standards but revolutionary for 1932. When the Denge station detected a contact, they immediately telephoned coordinates to neighboring stations at Hythe and Abbott's Cliff. Those stations would reorient their mirrors toward the reported bearing and attempt to confirm the contact. If 2 or 3 stations all achieved lock, the triangulation calculation could pinpoint the aircraft's location with surprising accuracy, within a few miles horizontally and a few thousand feet vertically. The network effect, Tucker's true innovation. Here's what most histories miss. Tucker's greatest achievement wasn't the concrete mirrors themselves, it was the coordinated network concept he developed for using them. Tucker created Britain's first integrated air defense information network. Multiple listening posts, connected by telephone, sharing data in real time to create a common operational picture of aerial threats. Standardized reporting protocols, centralized coordination centers that received reports from multiple stations and calculated positions. This network architecture, multiple sensors, data fusion, centralized coordination, became the foundational blueprint for radar networks. When Robert Watson Watt developed chain home radar in 1935 to 1940, he inherited Tucker's entire organizational framework and simply swapped acoustic sensors for electronic ones. The operators, the communication protocols, the calculation methods, the command centers, all came from Tucker's acoustic mirror program. The concrete ears failed, but the nervous system Tucker built to connect them succeeded brilliantly, becoming the template for modern air defense networks worldwide.
By 1933, Britain's acoustic mirror network stretched along the southeastern coast. Stations at Denge, Hythe, Abbott's Cliff, Kilnsea, and several other locations operated 24 hours a day, listening for threats from across the channel. The results were mixed. On clear, calm days, the system performed beautifully. In documented tests from 1933, operators at the Denge station successfully detected a Hawker Hart biplane at 18 miles distance. The crew at Hythe confirmed the contact seconds later. Triangulation placed the aircraft within a mile of its actual position. From initial detection to confirmed coordinates, 45 seconds. For 1933, this was extraordinary. No visual observation system could match it. No other technology in existence could detect aircraft beyond the horizon. But then the wind would pick up, and everything changed. On October 12, 1933, during a planned exercise, winds reached 25 miles per hour with gusts to 35. The Denge operators heard nothing until the test aircraft was just 7 miles offshore, giving only 4 minutes of warning. The massive 200-foot mirror became nearly useless, its huge surface area amplifying wind noise rather than aircraft engines. Weather wasn't just a limitation, it was a catastrophic weakness. The speed problem. During a December 1933 test, the RAF flew a new experimental fighter, a prototype that would eventually become the Hurricane, past the Denge mirrors at full throttle. The aircraft was traveling at approximately 300 miles per hour. The operators detected it at 12 miles. Simple mathematics revealed the disaster. 12 miles divided by 300 miles per hour equals 2.4 minutes of warning. Even if interceptors were already in their cockpits with engines running, they couldn't launch, gain altitude, and reach interception position in 2.4 minutes. As aircraft speeds increased,
acoustic mirrors became progressively less useful. The technology was being outrun by the very threats it was designed to detect. The Hythe ambiguity problem. Throughout 1934, operators struggled with a persistent issue. They could hear aircraft clearly, track their movements, calculate their bearing, but determining altitude remained maddeningly difficult. An aircraft at 5,000 feet, flying 10 miles away, sounded almost identical to an aircraft at 15,000 feet, flying 12 miles away. Defense commanders needed to know altitude to vector interceptors effectively. Sending a fighter to 5,000 feet when the bomber was actually at 15,000 feet meant the interceptor would climb through empty sky while the bomber sailed overhead unopposed. Tucker worked frantically on solutions. He experimented with multiple mirrors at different elevations, hoping the difference in detection characteristics would reveal altitude. He tried comparing signal strength from different dish sizes. Nothing produced consistent, reliable altitude information. The three-dimensional location problem, arguably the most critical requirement for air defense, remained only partially solved. The one spectacular success. On March 7, 1934, during a surprise test, the acoustic mirror network achieved something remarkable. A formation of 6 bombers launched from France at dawn, heading towards Dover with instructions to fly as quietly as possible, throttles reduced, engines at minimum power settings. The plan was to evaluate whether aircraft could sneak past the acoustic defenses. The Denge 30-foot mirror detected them at 17 miles. Within 90 seconds, Hythe and Abbott's Cliff confirmed. Triangulation placed the formation's position with extraordinary accuracy. RAF fighters scrambled from Biggin Hill. By the time the bombers reached Dover, 3 Hawker Fury interceptors were waiting at their exact altitude and location. The commanding officer of the bomber formation later wrote, "We genuinely believed we'd approach silently. We were quite shocked to discover we'd been tracked from 20 miles out. For a moment, we thought the British had developed mind reading." This test represented the acoustic mirror network at its absolute best. Experienced operators, optimal weather conditions, good communication, effective coordination, everything working perfectly. It would never be repeated. The February 26, 1935 demonstration. On a cold February morning, 2 men drove a van into a field near Daventry, about 100 miles from the coast. One was Robert Watson Watt, a Scottish physicist working for the National Physical Laboratory. The other was his assistant, Arnold Wilkins. They set up a receiver connected to an oscilloscope and waited. A Handley Page Hayford bomber flew overhead. The oscilloscope erupted with signals, radio waves bouncing off the aircraft's metal fuselage and returning to the receiver. Watson Watt had just demonstrated radar. The system wasn't affected by weather. Wind was irrelevant. The detection range was initially about 8 miles, but rapidly improved to 20, then 40, then 60 miles within months. It could detect aircraft day or night, in rain or fog, and crucially, it could determine distance with precision by measuring the time delay of the returning signal. Everything the acoustic mirrors struggled with, weather, altitude, range, speed, radar solved instantly. By June 1935, Watson Watt's experimental radar could detect aircraft at 40 miles. By September, the range reached 60 miles. By early 1936, it exceeded 80 miles. In December 1936, the Air Ministry formally canceled further development of acoustic mirrors and redirected all funding to radar. The concrete ears at Denge fell silent. Operators were reassigned. The enormous mirrors stood abandoned, monuments to a dead-end technology. But Tucker's legacy didn't die. What actually survived? When the Air Ministry established the chain-home radar network in 1937 to 1940, they needed a command and control structure. They needed communication protocols. They needed trained operators who understood air defense coordination. They needed a framework for how multiple detection stations should share information and create a unified operational picture. They copied Tucker's acoustic mirror network wholesale. The chain home stations used the same telephone communication systems Tucker had installed, the same reporting formats, the same centralized filtering and coordination centers. Many of the first radar operators were former acoustic mirror personnel who already understood the job. They just swapped earphones for oscilloscopes. The famous Dowding system that controlled RAF fighters during the Battle of Britain in 1940, its architecture came directly from Tucker's acoustic mirror network. Multiple detection stations feeding information to sector control rooms that vectored fighters to intercept threats. That entire concept originated with Tucker's coordination network for acoustic mirrors. The mirrors themselves became obsolete, but the nervous system Tucker built to connect them became the foundation of modern air defense. In a sense, Tucker didn't fail. He invented network-centric warfare before anyone had terminology for the concept. His concrete ears couldn't compete with radar, but his organizational innovations became permanent features of military operations worldwide.
Today, the 3 mirrors at Denge still stand. They're protected as historic monuments, sitting on an island in the middle of a disused gravel pit. The Royal Society for the Protection of Birds manages the site, offering occasional guided tours to visitors who want to see these alien structures up close. The mirrors have become cultural icons, featured in music videos by The Prodigy and Nicki Minaj, appearing on album covers for bands like Turin Brakes and Blank & Jones. They've been photographed thousands of times, mysterious concrete curves rising from the marsh like archaeological remnants from a forgotten civilization. But beyond their aesthetic appeal, the acoustic mirrors represent something profound about technological innovation. Sometimes your greatest achievement isn't the tool you build, but the system you create to use it. The network legacy. Modern air defense networks, whether they're guarding Washington, D.C., Moscow, or Tel Aviv, all descend from Tucker's acoustic mirror coordination system. The concept of multiple sensors feeding data to centralized coordination centers that then direct defensive forces is now universal in military operations. The U.S. military calls it network-centric warfare. NATO calls it collaborative engagement. The underlying concept remains identical to what Tucker pioneered in 1930. Connect your sensors, share your data, centralize your coordination, distribute your response. The operator legacy. The specialized skills Tucker's operators developed, distinguishing signal from noise, maintaining concentration during long periods of silence, and making rapid identifications from ambiguous data, these skills translated directly to radar operation, and later to sonar operation on submarines, and eventually to all forms of electronic warfare. The military discipline of sensor operator, as a specialized profession, traces its origins to Tucker's acoustic mirror program. Before Tucker, military observers were just people looking through binoculars. After Tucker, sensor operation became a technical specialty requiring extensive training and rare aptitude. The failure that taught success. Perhaps most importantly, the acoustic mirror program demonstrated something crucial about military technology development. Don't fall in love with your solution. When Watson Watt demonstrated that radar solved the same problems better, the Air Ministry didn't stubbornly cling to acoustic mirrors because of sunk costs. They recognized the superior technology and pivoted immediately. That institutional flexibility, being willing to abandon an enormous investment when something better emerges, arguably saved Britain during World War II. If the Air Ministry had insisted on perfecting acoustic mirrors for another 5 years before considering radar, Britain might have entered the war without an effective early warning system. Tucker himself never expressed bitterness about radar making his work obsolete. In post-war writings, he focused on how his coordination network concepts contributed to chain home success. He understood that technology programs don't fail when they're replaced by something better. They succeed by pushing the state-of-the-art forward until someone makes the next breakthrough. Modern acoustic sensing. Interestingly, acoustic sensing actually didn't die. Modern military forces use sophisticated acoustic sensors for detecting artillery fire,
locating snipers and tracking helicopters in urban environments. The U.S. Army's Boomerang system, deployed in Iraq and Afghanistan, uses an array of microphones to detect incoming gunfire and calculate its origin point within seconds. The same triangulation principles Tucker developed, just underwater instead of in air. Submarine warfare relies extensively on acoustic sensing. Passive sonar systems detect enemy vessels by listening for propeller noise, exactly the principle Tucker used, just underwater instead of in air. The technology didn't become obsolete, it found different applications where acoustic sensing offers advantages over electromagnetic detection. The concrete monument. The Denge mirrors stand as reminders of a transitional moment in military history, the brief window when human hearing, amplified by concrete and geometry, represented the cutting edge of defense technology. They also remind us that breakthrough innovations rarely arrive fully formed. Radar didn't spring perfectly developed from Watt's imagination. It emerged from a military establishment that had spent 20 years struggling with acoustic detection, understanding exactly what capabilities an early warning system needed and recognizing immediately when someone invented a technology that met those requirements better than anything that had come before. The acoustic mirrors were the ladder that Britain climbed to reach radar. Once they reached the top, they kicked the ladder away, but they couldn't have reached that height without it.
So what can we learn from 3 concrete monsters slowly weathering away on the Kent coast? First, the importance of pushing forward even when you're on the wrong path. Tucker's acoustic mirrors were ultimately a technological dead end, but the journey taught Britain's military establishment crucial lessons about sensor networks, operator training, and information coordination. Without those lessons, they couldn't have deployed radar effectively when it arrived. Second, the difference between solving the right problem and building the right tool. Tucker correctly identified the problem, detecting aircraft beyond visual range, and he correctly identified what capabilities a solution needed: long detection range, all-weather operation, accurate location data, and networked coordination. His tools weren't perfect, but his problem analysis was flawless. When radar arrived, the Air Ministry knew exactly what questions to ask about its capabilities because Tucker had already framed the problem correctly. Third, the hidden innovations often matter more than the flashy ones. Everyone remembers radar. Almost nobody remembers Tucker's coordination network, but that network concept has influenced military operations for nearly a century, while radar technology has been completely transformed multiple times. The acoustic mirrors also offer a poignant reminder about military service. Dozens of operators spent years in concrete chambers beneath those dishes, staring into darkness, listening to static, performing a mission that history would classify as obsolete within months of their training completion. Their work has been completely forgotten. But those operators were the first generation of technical warfare specialists, the ancestors of every radar operator, sonar technician, and sensor analyst who followed. They invented a profession that didn't previously exist. They developed skills nobody had needed before. They proved that electronic warfare required not just better technology, but differently trained personnel. That's a legacy worth remembering. Your next steps. If this story of technical problem-solving and military innovation fascinates you, we've got more content you'll love. Next week, we're exploring how Allied codebreakers at Bletchley Park solved the impossible Enigma machine using mechanical computers built from bicycle parts and telephone relays. Another story where the organizational innovations mattered more than the technology itself. If you enjoyed this deep dive into acoustic detection, hit that subscribe button. We publish new military history content every week, focusing on the engineering problems and technical solutions that changed warfare. The stories that traditional history books skip over. Drop a comment telling us what other pre-radar detection technologies should we investigate. We're considering episodes on World War I sound ranging for artillery, naval acoustic torpedoes, or submarine sound detection. Let us know what interests you most.
And if you really want to appreciate how different military technology was before electronics, check out our video on mechanical fire control computers, the analog calculating machines that let battleship guns hit targets 10 miles away using nothing but gears, cams, and differential equations. The concrete years at Denge heard bombers approaching 20 miles away, 12 minutes before radar existed. They couldn't compete with the electronic revolution that followed, but they proved something important. Human ingenuity, combined with acoustic physics, could reach beyond the horizon. The mirrors may be obsolete, but the operators who learned to listen through them taught every generation of sensor operators that followed. Sometimes the quietest signals carry the most important warnings. Thanks for watching. We'll see you next week.